Hello learners, Quality Engineering and Management, Week 6, video number 21. The topic is Taguchi Method, presented by Dr. N.Venkateshwarlu, Associate Professor, Mechanical Engineering, School of Engineering and Technology, IGNOU, New Delhi. Learners, Taguchi Method. Taguchi methods were developed by Dr. Junichi Taguchi after World War II in sharp contrast with statistical quality methods in which the process quality is being monitored online, that is during the production. Taguchi's offline methods focus on design and attempt to determine best conditions of design parameters which results in superior performance of the product. Taguchi calls his design approach as a parametric design approach. Objectives. Learners, after listening to this video lecture, you will be able to understand Taguchi's offline quality improvement method, explain Taguchi's concept of loss function, describe parameter design, discuss on signal to noise ratio, understand Taguchi's tolerance design, differentiate between Taguchi and Deming's philosophy on quality improvement. These are the various objectives we are going to discuss in this video lecture. Taguchi loss function. Taguchi's concept of loss function is focused on loss faced by the customers. According to Taguchi, the customer suffers from loss not only when product characteristics are outside specification, but whenever it deviates from its target value. Out of specification is the common measure of quality loss. It indicates the products that meet specifications are good, otherwise not acceptable. However, the customer does not always appreciate this concept. For him, the product that meets specifications is as good as the product that is barely out of specifications. Here, the Taguchi loss function says that whenever the product deviates from the target value, it is a loss to the customer. So that is the Taguchi's loss function. For example, if one has to choose 100 steel tubes 20 mm, it is important that the size of tubes are normally distributed with target centered on 20 mm. Though some sizes may cross the specified limits, the loss function combines the cost, target and variation into one entity. The losses includes failure to meet customer requirements. Taguchi developed many loss functions, among which the quadratic function is the most common. This loss function is also called nominal the best. So in this, the Taguchi loss function, the loss L when performance Y of a product deviates from the target T is Ly, that is equal to K into Y minus T whole square, where K is equal to A by delta square or D square, where D is the specified tolerance and A is the loss to the customer. As illustrated in figure 6.10, the loss to customer is proportional to the square of the deviations of the parameter from its target value, and the least value of loss is 0 when performance characteristics matches with the target. Hence, this loss function is called nominal the best. So this is the figure Taguchi loss function. Here it shows that here the T is the target value, and if this curve deviates from the target value and it reaches at the tolerance, that is T minus delta or T plus delta, then it will be in the tolerance limits and no loss will be taken place during this period. But if it moves away from this target value and how much ever it is moving, the total will be the loss for the customer. So that's what the Taguchi's loss function states. Here you can observe this left side, it will be T minus delta and for it will give the loss, and in the right side T plus delta, and from there to right side it gives the total loss to the customer. This is the Taguchi's loss function. Taguchi's loss function, the one is the smaller the better and B is the larger the better. So for that also you can see that this is the smaller the better graph. Here the performance characteristics, it will move away from the target value, and here in larger the better. So here it will move from, you can say, maximum y, where the y maximum will be there, from there it will move towards the 0. So that is the difference between the smaller the better and the larger the better loss function. The Taguchi's loss function, as seen in the figure 6.11a, the target value for smaller the better is 0 and there are no negative values for the performance characteristics. Example of performance characteristics are pollution from the automobile, out of round for a hole, etc. The third loss function is larger the better. This function becomes applicable in the case of such as mileage, strength of a weld, etc. These are the examples. Then figure 6.11b shows that zero loss value is obtained when target value of infinity. The loss function is given by Ly, that is equal to k into 1 by y square, where k is equal to ay square. Then parameter design. Parameter design by Taguchi method is an offline quality control method to make a process robust against source of variation and hence improve performance. Taguchi recognized that factors affecting the product's functional characteristics can be grouped into control factors and noise factors. These factors also called as a control factors and uncontrolled factors also. Control factors are known factors or variables and can be easily controlled by the designer or design engineer. For example, in a plant, the process engineer can easily adjust variables like pressure and temperature to produce a chemical. So in this parameter design, what the Taguchi says that here he will one has to identify the controllable factors and uncontrollable factors. Here these two are controllable factors, also known as a signal factors, and then uncontrollable factors are noise factors. On the other hand, noise factors are variables such as environmental variables, deterioration and manufacturing variations that are difficult and expensive to control. If noise factors are eliminated, then the process can always be maintained at nominal value. However, Taguchi proposed that instead of finding and eliminating noise factor, the impact of noise factor should be reduced. So this is the Taguchi's parameter design function. So the designer therefore has to identify components of design that most influence the desired outcome of the design process. This is a very cost-effective technique to improve product quality. This can be realized by selecting the optimal combination of factor levels that makes the process less sensitive to the effects of noise factors. The parameter design. Taguchi's method for identifying settings of design parameters that maximize performance characteristics, that is yield or productivity, is summarized below. So first it is step by step one has to learn. In the first step, identify initial settings of design factors or parameters and identify important noise factors and their ranges. Here both factors one has to identify, design factors and the noise factors. Then construct design and noise matrices and plan the parameter design experiments. Two levels of each design and noise factor are used to construct a matrices. The usual rule is to set one level as low, coded as 1, and the other as high, coded as 2. The procedure is to alter each design parameter and noise factors to its highest and lowest selected value and obtain the result of each combination. So here what it says that in the parameter design process, one has to identify the design factors and noise factors. This noise and which are to be tested at the two levels, at the low level and the high level, so that by doing various combination, the effective combination parameters can be selected so that the best results will be achieved. The set of combinations of factors that gives the best results is selected as the design parameters of the final product. For example, consider that 3 factors in a process can be controlled. This gives rise to 8 possible combinations. For the purpose of experimentation, consider that the noise factors can be controlled and changed. With 2 noise factors, a total of 4 combinations are constructed. So in the here in the example, it says that the 3 design factors will be selected, and which can be by combination, it will give 8 combinations. And in the noise factors, we are taking only 2 factors, and here the 4 combination can be constructed. So here by seeing this parameter design, these matrices, here the design matrix consists of 3 factors with 8 levels. So it gives 8 factors, and then here in the noise factor, noise matrix, 2 factors will be there and 4 combinations will be constructed. So thus a total 8 into 4, it is equal to 30 different experiments can be conducted. These 32 experiments allow a designer to evaluate the effect of noise factors on each controllable factor setting and determine the one setting that minimizes the variability. So by doing 32 experiments, we can get only one highest performance factors or combination, so that will be the best combination of a parameters, best combination of a factors which will influence or which will enhance the efficiency of a product or a process or minimizes the defects. Parameter design. Conduct the parameter design experiments and obtain an observation at each setting. The next step is to evaluate the observations against some performance measures or the performance of a system. The performance measure, the signal to noise ratio, is an ideal metric for the purpose of performance measurement. The signal represents the amount of energy for an intended function, and the noise represents the amount of energy wasted. Signal factors are set by designer to obtain the intended value of the response variable. So that is the mean y bar of the any characteristics. Performance measure. Noise factors are not under control or expensive to control. The variance S square is used to measure noise. For a loss function of nominal the best type, the signal to noise ratio is given by S by n is equal to 10 log 10 y minus square by S square minus 1 by n. This is the equation where n is the number of observations, the unit of measurement of signal to noise ratio is decibels. The signal to noise ratio for a loss function of smaller the better type is S by n is equal to minus 10 log 10 sigma y square by n. The signal to noise ratio for a loss function of larger the better type is S by n, that is equal to minus log 10 sigma 1 by y square divided by n. So these 3 equations we can taken for the smaller the better, larger the better, and nominal the better. Consider the following example. A food packaging producer is comparing the caloric content of a original process with a new process. Which process has the lowest content and what is the difference? The results. So here we can find out by taking an example which one is the lowest content and what is the difference we have to find out. So for that we have taken the results are original process parameters we have taken here are 130, 135, 128 and 127. Then new process parameters are 115, 112 and 120, 113. Then the signal to noise ratio, smaller the better, should be used to compare the calorie content. For original process, we can find out by substituting in the equation, that is signal to noise ratio minus 10 log 10 into 130 whole square plus the original ones we have to take here, the 130 square plus 135 square plus 128 square plus 127 square whole divided by 4, that is equal to minus 42.28 decibels. And for the new process, signal to noise ratio, that equation is minus 10 log 10 into 115 square plus 112 square plus 120 square plus 113 square whole divided by 4, that is equal to minus 41.22 decibels. The difference is the 1.06 decibels. This indicates that the new process packs less calories. So that is the advantage of this performance measurement or Taguchi's loss function or signal to noise ratio. Then Taguchi's tolerance design. Then first we have find out the Taguchi's performance measurement. Again now we have to test the Taguchi's tolerance design. The tolerance design is the selective tightening of the tolerance to eliminate excessive variations. It uses the analysis of variance ANOVA to determine with factors contributing to the total variability and the loss function to trade off between quality and cost. The method of determining the percent contribution of factors to the total variability is illustrated via an example. So here we are taking Taguchi's tolerance design. So here ANOVA test one has to conduct. So for that we have to take various factors and which are the factors are more influencing the process, that we have to identify. So by taking one example to find out the tolerance, the Taguchi's tolerance design, the ABC Industries produces iron tube by casting process. However, the castings require extra grinding to machine of extra material. 7 factors were found to influence the cast. One is sand compactness, 2 iron temperature, 3 clay addition, 4 mold hardness and 5 mulling time, and 6th one is sea coal addition and 7th one is sand addition. So here we have selected 7 factors which are influencing on the production of a casting process. Taguchi's tolerance design. In order to determine which factors contribute most, 2 levels of each factor was considered for experimentation. 8 treatment conditions were taken as shown in table 6.5 and the percentage of castings that required finish grinding are shown in the last column. That is, for treatment condition 1 with all the 7 factors at level 1, 89% of the castings required grinding. By seeing table you can understand this, what is this 89%. So by seeing this table, treatment condition for iron castings. Here the treatment conditions are 8 conditions are there, 8 times low, high, high, low, like that we have various combinations are there. So treatment condition combinations. Here the various 7 factors we have identified and that 7 factors also to be treated, which factor is influencing more. So the treatment condition, which treatment condition, how much percentage is required, how much percentage of materials produced or casted materials are required grinding. So here it is shows that for the TC1 it is 89%, means 89% of these components which need the grinding. So in the second means treatment condition 2, so it requires a high level we will conduct the test, so that here it is 55% of casted materials need grinding. Like that various stages, it is for 8th stage, 8 level, it requires 55% of casted materials need grinding. The step 1, the sum of the squares of each factors are calculated by sum of SSA, the sum of squares for A, that is equal to sigma A square by n minus T square by n, that is equal to squares of sum of first level response divided by number of first level plus squares of sum of second level response divided by number of second level minus squares of sum of all responses divided by total number of all levels, that is equal to, here we have got all the 7 factors and 8 levels, we have got the various values that we have to substitute. So then we will get the value 89 plus 55 plus 38 plus 44 and so on. So we will get the value is equal to 200. Similarly, the sum of squares for other factors are obtained as sum of squares for C is equal to 882, sum of squares for D is equal to 1404.5 and sum of square for E is equal to 312.5 and sum of square for F is equal to 1152 and sum of square for G is equal to 32. So like this we have to find out sum of square for each factor. In the step 2, calculate the mean square for each factor as MS, that is equal to SS by degree of freedom, where degree of freedom is equal to degrees of freedom is equal to number of levels minus 1, that is equal to, here we have taken 2 levels, low and high, so that the 2 levels are there, 2 minus 1, that is equal to degree of freedom is equal to 1. Then step 3, tabulate the SS and MS in the ANOVA table as shown in table 6.6. Calculate F using the pooling technique. The pooling up procedure is to test the factors with smallest SS against the next largest. If not significant, the SS is pooled and tested against the next largest target. The process is continued until a factor is significant or 1/2 of the total number of degrees of freedom. The calculation at first step is done with A and G, that is equal to F is equal to MSG by MSE, that is equal to SSG by degree of freedom and SSE by degree of freedom, that is equal to 32 by 1 divided by 4.1 by 1, that is equal to 7.11. To calculate F value, for pooling technique, it gives a 7.11. This value is compared against the F value obtained in the table 6.7. The F value is obtained corresponding to the degree of freedom of the numerator and denominator. Thus, the critical value of F for A and G is 161. Hence, the factor A is not significant. Now, the next largest target is B. To calculate F, the last 2 factors are pooled. Then F is equal to MSB by MSA plus G, that is equal to SSB by degree of freedom and SSA plus G by degree of freedom, that is equal to 10.95. From F tables, the critical value for 1 and 2 degree of freedom is 18.5, which is greater than the calculated value. So the factor B is also not significant. Then factor B when pooled with A and G gives MS A plus G plus B, that is equal to SS A plus G plus B by degree of freedom, that gives 78.8. However, since half the total degrees of freedom, that is 7, has been used, hence pooling process is over, the F value for remaining factors C, D, E and F are obtained by dividing the MS of each factor by the last pooled MS of factors A, G and B. Hence FC is equal to MSC by MS A plus G plus B, that is equal to 882 by 236 by 5, that is equal to 11.2. Similarly, we have to calculate FD 17.8, FE 4 and FF is equal to 4.6. Since the critical value corresponding to 1 and 3 degrees of freedom is 10.1. Hence, factors C, D and F are significant at 95% confidence and E is not, because E value is it is 4 only. Step 5. Calculate SS bar or pure SS by subtracting the pooled error from the SS for factor C. Sum of square. SS means sum of squares for C, that is equal to SS bar C, that is equal to SS minus into bracket MS A plus B plus G into degree of freedom for C, that is equal to 882 minus 78.8 into 1, that is equal to 803.2. In the step 6, the calculate percent contributions by the dividing the SS dash of each factor by the total SS dash. From table 6.6, it is observed that the factor D contributes the most. The contribution of pooled factors is 13.8%, which is satisfactory. So, if the error had been around 40%, it would indicate the omission of important factors or inadequate measurements. So, this is the ANOVA table. Here you can find out degree of freedom and mean squares and sum of squares, then F value and SS dash value and then percentage. So, the pooled A plus G plus B at a degree of freedom 3, it gives the sum of squares is 236.5 and the mean square is equal to 78.8 and it gives the percentage of acceptance is equal to 13.8. So, this is the importance of the Taguchi's signal to noise ratio and design function. Then F table also, similarly with we will compare with F table. So, in the F table also it gives the values which are acceptable. Then comparison of Taguchi with Deming approach. The basic difference between the Taguchi and Deming's philosophy on quality improvement lies in the way of representing loss. Deming acknowledged that variation is a process exists and cannot be eliminated completely due to presence of unknown factors. Taguchi wanted to find a useful way of representing the loss caused by these unknown factors with statistics. Hence, he proposed the loss function and showed that any item manufactured away from the nominal would result in some loss to the customer or the wider community. These losses could come through early wear out, difficulties in interfacing with other parts, etc. In other words, Taguchi stressed on the need to produce an outcome on target, for example, to machine a hole to a specified diameter. The approach of Deming towards quality was focused on deriving maximum benefits with the existing resources. The 14 points of Deming set the basis for management for improvement of quality, productivity and competitive position. He advocated for a uniform policy on quality that must be practiced by all associated with an organization. That is the difference between the Taguchi and Deming's approach. Deming's teachings ask for coordinated efforts among the various layers of organization to fulfill one common objective, that is customer satisfaction. Taguchi, on the other hand, argued that the quality engineering should start with the elimination of variation from the design stage onwards. Hence, he considered the prospects of using design of experiments to understand the influence that parameters had on variations. So, this is the two differences of two quality gurus about the quality improvement process. Learners, conclusions. I hope you understood the concept of Taguchi's loss function, Taguchi's parameter design, tolerance design, performance measure and comparison Taguchi's and Deming's philosophy of quality improvement. Thank you.